What if I told you that right now, as you're settling into this moment, there are 7 people living 250 miles above your head, traveling at 5 miles per second, witnessing 15 sunrises and sunsets every single day? In this exploration, we'll uncover the most ambitious project humanity has ever attempted. A structure so complex, it required more than 40 assembly flights to build. A laboratory so advanced, it has hosted over 4,000 experiments that push the boundaries of science itself. But before we begin this journey through the cosmos, feel free to comment your time and location below. It's always incredible to know that we're all scattered across this small blue planet, looking up at the same sky, where something truly magnificent orbits above us. The visuals are here for you, but there's absolutely no problem if you doze off midway through this cosmic voyage. Feel free to close your eyes, breathe deep, and let your imagination float weightlessly through space. Also, if you find comfort in these gentle explorations of science and human achievement, I'd be grateful if you'd consider subscribing and liking this video. It would mean the world to me. Let's begin this extraordinary journey to humanity's greatest achievement. Welcome to everything you need to know about the International Space Station. Picture this moment. You're looking up at the night sky, and somewhere in that vast darkness, a structure the size of a football field is silently racing overhead. It's moving so fast that it completes an entire orbit of Earth in just 90 minutes. Inside this remarkable machine, human beings are conducting experiments that could cure cancer, unlock the mysteries of the universe, and prepare us for journeys to distant worlds. This isn't science fiction. This is happening right now, and it represents the pinnacle of what we can achieve when nations set aside their differences and reach for the stars together. The International Space Station is more than just a marvel of engineering. It's a testament to human cooperation on a scale never before attempted. Imagine bringing together former Cold War enemies and allies in a project so complex that it requires constant coordination across multiple continents, time zones, and cultures. Picture mission control centers operating around the clock in Houston, Moscow, Munich, and Montreal, all working in perfect harmony to keep 7 people alive in the most hostile environment imaginable. But here's what makes this story truly extraordinary. This project didn't happen overnight. It represents decades of dreaming, planning, and building something that many thought was impossible. The International Space Station is the result of 5 space agencies from different corners of the world coming together with a shared vision. The United States, Russia, Europe, Japan, and Canada each contributed their unique expertise, resources, and capabilities to create something greater than any nation could achieve alone. Tonight, we're going to explore every aspect of this incredible achievement. We'll journey through the history of how this floating laboratory came to exist. We'll discover what daily life is like for the brave souls who call this place home. We'll uncover the groundbreaking science that's happening 250 miles above our heads. And we'll understand why this structure represents humanity's first permanent foothold in the cosmos. The story begins with a vision that seemed almost impossible to achieve. In the aftermath of the Cold War, when trust between nations was fragile and space exploration was driven by competition rather than cooperation, someone dared to imagine something different. What if instead of racing against each other to reach the stars, we worked together, What if we combined our knowledge, our resources, and our dreams to build something that would benefit all of humanity? This vision became reality when construction began in the late 1990s. But calling it construction doesn't capture the true magnitude of what was accomplished. Imagine trying to build a complex structure while floating in the vacuum of space, where there's no air to breathe, where temperatures can swing from 250 degrees Fahrenheit in sunlight to minus 250 degrees in shadow, and where every tool, every bolt, every component must be carefully controlled to prevent it from floating away into the void. The first piece of this cosmic puzzle was launched on November 20th, 1998. A Russian module called Zarya, which means sunrise in Russian, began its journey to space aboard a Proton rocket. This wasn't just any launch. This was the foundation stone of humanity's greatest construction project. 2 weeks later, the Space Shuttle Endeavour carried Unity, the first American component, to rendezvous with Zarya in the darkness of space. Picture the precision required for this cosmic dance. 2 massive spacecraft, each traveling at thousands of miles per hour, had to meet in the vast emptiness of space with accuracy measured in inches. Astronauts in bulky spacesuits, working in the vacuum of space, connected these modules together using tools and techniques that had never been attempted on such a scale. This was just the beginning of a construction project that would span more than a decade and require the most complex choreography ever performed. For the next year and a half, this basic 2-module structure orbited Earth unmanned, waiting for the next phase of assembly. Then in July 2000, the Russian module Zvezda joined the growing station, providing the life support systems necessary to sustain human life. Finally, on November 2nd, 2000, the first permanent crew arrived aboard a Russian Soyuz spacecraft. 3 people, American astronaut Bill Shepard and Russian cosmonauts Yuri Gidzenko and Sergei Krikalev, became the first residents of humanity's outpost in space. That moment, 25 years ago, marked the beginning of an unbroken chain of human presence in space that continues to this day. Every single day since November 2nd, 2000, humans have been living and working aboard the International Space Station. Through changes in government, through international tensions, through pandemics and global challenges. This symbol of human cooperation has remained steadily operational, proving that when we work together, we can achieve the impossible. But what exactly did we build up there? The International Space Station is essentially a city in space, with the complexity of a modern skyscraper compressed into a structure that must survive the vacuum of space, extreme temperature variations, and constant bombardment by microscopic meteoroids. The station consists of 16 pressurized modules, connected by a massive truss structure that serves as the backbone of the entire complex. This truss isn't just structural support, it's a technological marvel in its own right, spanning 356 feet from end to end and housing the power generation systems that keep the station alive. 4 enormous sets of solar panels track the sun as the station orbits, generating enough electricity to power the equivalent of 40 homes on Earth. These panels must constantly adjust their orientation as the station travels its orbital path, ensuring maximum power generation during the brief periods when they are exposed to sunlight. The pressurized modules themselves represent decades of engineering innovation. Each one had to be manufactured to exacting standards, designed to maintain Earth-like atmospheric conditions while withstanding the harsh environment of space. The Russian segment includes modules like Zarya, which initially provided power and propulsion, and Zvezda, which serves as the primary living quarters for crew members. The American segment features laboratory modules, storage areas, and connecting nodes that allow the station to function as a cohesive unit. These modules are marvels of space engineering, designed to provide breathable atmosphere, comfortable temperatures, and protection from radiation while floating in the vacuum of space. Each module represents years of development, testing, and refinement, with backup systems for backup systems to ensure that the 7 people living inside remain safe and healthy. But perhaps the most remarkable aspect of the International Space Station isn't its technology or its size. It's the people who live there and the work they do. Since that first crew arrived in November 2000, 290 individuals from 26 countries have called the station home. These aren't just astronauts and cosmonauts. They're scientists, engineers, teachers, and explorers who represent the best of humanity's spirit of discovery. Living aboard the International Space Station requires adaptation to an environment where up and down have no meaning, where water forms floating spheres instead of flowing downward, and where every movement must be carefully controlled to avoid floating into walls or equipment. Crew members must adapt to sleeping while strapped into sleeping bags attached to walls, eating rehydrated meals from pouches, and exercising on specialized equipment designed to work in weightlessness. The psychological challenges are equally demanding. Imagine living in isolation, confined to spaces smaller than most homes, separated from Earth and loved ones by 250 miles of vacuum. The mental fortitude required to thrive in such conditions while maintaining peak performance in critical scientific work is extraordinary. Yet crew members consistently describe their time in space as transformative, offering perspectives on life and humanity that can only be gained by seeing Earth from space. Each day aboard the station follows a carefully choreographed schedule planned down to 5-minute increments by teams of mission controllers around the world. A typical day begins at 6 a.m. Greenwich Mean Time and continues until 9:30 p.m., including 3 meals and 2.5 hours of mandatory exercise. But calling it a typical day doesn't capture the reality of life in space, where no 2 days are quite the same, and where crew members must be prepared to handle anything from routine maintenance to emergency situations. The work performed aboard the station falls into several categories, each critical to the mission's success. Scientific research forms the core of station operations, with crew members conducting experiments that take advantage of the unique microgravity environment to study everything from protein crystallization to combustion physics. These aren't abstract academic exercises. The research conducted aboard the station has direct applications for improving life on Earth, from developing new medical treatments to designing more efficient engines. Maintenance work is equally important and far more complex than it might sound. The International Space Station is essentially a machine with hundreds of thousands of components, all of which must function perfectly to keep the crew alive. Systems that fail on Earth can be quickly repaired or replaced. In space, crew members must be capable of diagnosing and fixing problems with life support systems, computers, scientific equipment, and structural components, using only the tools and spare parts available on the station. This is where our journey through humanity's greatest achievement truly begins. We've touched the surface of what makes the International Space Station extraordinary, but there's so much more to explore. The science being conducted up there is revolutionizing our understanding of medicine, physics, and biology. The international cooperation required to keep it operational provides lessons for addressing challenges here on Earth. And the technologies being developed and tested aboard the station are paving the way for humanity's next giant leaps into the cosmos. As we prepare to dive deeper into this remarkable story, remember that everything we're about to discover is happening right now, 250 miles above your head. While you're reading these words, 7 people are conducting experiments that could change the world, maintaining systems that keep them alive in the vacuum of space, and pushing the boundaries of human knowledge and capability. The daily routine aboard the International Space Station reveals the extraordinary nature of ordinary life in an extraordinary place. Imagine waking up, not to the gentle pull of gravity drawing you from your bed, but to an alarm that interrupts dreams of weightlessness that many astronauts experience floating in their sleeping quarters. There's no stumbling to the bathroom or shuffling to the kitchen. Instead, crew members must carefully orient themselves in 3-dimensional space, where walls become floors and ceilings become launching points for graceful movements through the station's corridors. But here's what makes this morning routine truly fascinating. While you experience one sunrise and sunset each day, these space residents witness 15 complete day-night cycles as they race around our planet. Every 90 minutes, they watch the sun rise over Earth's curved horizon, illuminating continents and oceans in brilliant detail, then set again as they pass into the planet's shadow. This constant cycle of light and darkness could easily disrupt human circadian rhythms, those ancient biological clocks that have evolved over millions of years to match Earth's 24-hour rotation. The solution demonstrates the careful attention to human physiology that makes long-duration spaceflight possible. Mission planners maintain artificial day-night cycles aboard the station, using lighting systems and scheduled activities to help crew members maintain normal sleep-wake patterns. Without this careful management of their biological rhythms, astronauts would quickly find themselves in a state of permanent jet lag, unable to perform the precise scientific work and critical maintenance tasks that keep the station operational. Exercise becomes not just recreation, but a medical necessity in this weightless environment. Without gravity's constant pull, the human body begins to change in ways that would be devastating for long-term health. Bones lose density at rates comparable to severe osteoporosis. Muscles atrophy as they're no longer needed to support body weight against gravity's relentless downward force. The cardiovascular system, accustomed to pumping blood against gravity, begins to decondition as bodily fluids redistribute throughout the body. The station's exercise equipment represents ingenious engineering solutions to the challenge of working out in weightlessness. Traditional weights would be useless in microgravity, so engineers developed systems using vacuum cylinders and flywheel technology to provide resistance. Astronauts strap themselves to treadmills that use bungee cords and harnesses to pull their bodies downward, simulating the act of running. They perform squats and deadlifts using specialized devices that create artificial resistance through mechanical systems that work even when floating in space. This daily exercise routine isn't optional. Crew members spend approximately 2 hours each day maintaining their physical condition, not for fitness, but for survival. Without this rigorous regimen, astronauts would return to Earth so weakened by muscle loss and bone deterioration that they might be unable to stand or walk. Some astronauts have described the sensation of exercising in space as strange and surreal, strapping themselves to machines and working against artificial resistance, while floating in an environment where physical effort feels different from anything experienced on Earth. Meals aboard the station reveal another fascinating adaptation to life without gravity. Food must be carefully packaged to prevent crumbs or liquids from floating away and potentially interfering with sensitive equipment or being inhaled by crew members. Water doesn't pour from containers, but instead forms perfect spheres that float through the air until they contact a surface. Salt and pepper come in liquid form because granules would float away and could clog air filters or damage electronic systems. The dulling of taste buds in microgravity creates unexpected culinary preferences. Foods that might seem overly spicy or strongly flavored on Earth become appealing to astronauts whose sense of taste is diminished by the effects of weightlessness. This physiological change means that menu planners must consider not just nutritional requirements, but also the enhanced flavoring needed to make meals appealing to crew members whose taste perception has been altered by their environment. Preparation and consumption of meals becomes a careful choreography of opening packages, adding water to rehydrated foods, and ensuring that every particle of food is controlled and contained. Drinking requires special containers with straws and valves to prevent liquids from escaping into the cabin atmosphere. Even the simple act of eating requires new techniques adapted to an environment where food doesn't stay on plates and beverages don't stay in cups. The scientific work conducted aboard the station represents the primary purpose of this remarkable facility. More than 4,000 experiments have been performed in the unique microgravity environment, taking advantage of conditions that cannot be replicated on Earth. When gravity's influence is removed, fundamental processes behave differently, revealing new insights into physics, biology, chemistry, and materials science. Protein crystallization experiments demonstrate the profound impact of microgravity on scientific research. On Earth, gravity causes convection currents and settling effects that interfere with the formation of perfect crystal structures. In space, proteins can form larger, more organized crystals that reveal molecular structures with unprecedented clarity. These improved crystal structures enable researchers to better understand how proteins function and how they might be modified to create more effective medications. The development of new medicines for cancer, muscular dystrophy, and neurodegenerative diseases has been advanced through protein research conducted in the station's laboratories. Scientists can grow high-quality crystals that provide detailed molecular blueprints for drug development, potentially leading to treatments that would be impossible to develop using Earth-based research alone. Stem cell research takes on new dimensions in the microgravity environment. Without gravity's influence, stem cells can be grown in greater quantities and with characteristics that differ from those produced on Earth. These space-grown cells show enhanced potential for regenerative therapies that could treat neurological, cardiovascular, and immunological conditions. The implications extend far beyond space medicine to applications that could benefit millions of people suffering from degenerative diseases. Combustion research aboard the station has revealed phenomena that exist only in microgravity. Cool flames, which burn at lower temperatures and produce different chemical reactions than traditional flames, cannot be sustained on Earth because gravity causes hot gases to rise and disrupt the combustion process. In space, these cool flames can burn steadily, providing insights that could lead to more efficient engines and cleaner combustion processes for applications ranging from automotive engines to power generation systems. The study of fluid physics in microgravity offers insights that improve everything from fuel injection systems to medical devices. Without gravity's influence on fluid behavior, researchers can observe how liquids behave based purely on surface tension, viscosity, and molecular forces. These observations lead to better understanding of fluid dynamics that has practical applications in designing more efficient industrial processes and medical equipment. Materials science experiments take advantage of microgravity to create alloys and composites with properties that cannot be achieved on Earth. When metals are melted and allowed to solidify in weightlessness, they form structures without the settling and segregation effects caused by gravity. These space-processed materials often exhibit superior strength, uniformity, or other desirable characteristics that could lead to advances in manufacturing and engineering applications. The station serves as a unique platform for Earth observation and atmospheric research. From their vantage point 250 miles above the planet's surface, crew members can observe weather patterns, natural disasters, and environmental changes with perspectives impossible to achieve from ground-based locations. This research contributes to climate science, disaster response planning, and environmental monitoring efforts that help protect and preserve our planet. Fundamental physics experiments aboard the station push the boundaries of human understanding about the nature of matter and energy. In the microgravity environment, scientists can create and study exotic states of matter like Bose-Einstein condensates, which exist at temperatures near absolute zero and behave according to quantum mechanical principles rather than classical physics. These experiments contribute to our understanding of quantum mechanics and could lead to revolutionary technologies in computing, communications, and energy production. The psychological and social aspects of long-duration spaceflight provide valuable insights for future missions to the Moon, Mars, and beyond. Living in isolation and confinement while performing demanding work under constant scrutiny requires mental resilience and interpersonal skills that are crucial for the success of deep space exploration missions. The lessons learned from decades of crew operations aboard the station inform the selection, training, and support of astronauts who will one day journey to distant worlds. As we delve deeper into the remarkable story of humanity's greatest collaborative achievement, we begin to understand that the International Space Station represents far more than advanced technology and scientific research. It embodies our species' capacity to overcome seemingly insurmountable challenges through cooperation, ingenuity, and unwavering determination to push beyond the boundaries of what was previously thought possible. The station's role as a testing ground for future exploration reveals perhaps its most profound purpose. Every system, every procedure, every lesson learned about human survival in space contributes to humanity's preparation for journeys that will take us far beyond Earth's protective embrace. The technologies being developed and refined aboard the station today will enable the first human missions to Mars, the establishment of lunar bases, and eventually our expansion throughout the solar system. Life support systems aboard the station demonstrate remarkable efficiency in recycling the basic necessities of human survival. Each crew member requires approximately 2.7 kilograms of water daily and breathes the equivalent of 0.9 kilograms of oxygen. Rather than constantly resupplying these essential resources from Earth, the station's environmental systems recycle wastewater from multiple sources, including humidity condensed from the air and even urine, purifying it through sophisticated filtration and treatment processes until it becomes cleaner than most municipal water supplies. The psychological impact of seeing Earth from space creates what many astronauts describe as a profound shift in perspective. From their unique vantage point, political boundaries disappear, and our planet appears as a single, fragile oasis suspended in the cosmic darkness. This overview effect, as it has come to be known, often transforms how crew members view their role as human beings and their responsibility to protect and preserve the only world we currently call home. The delicate dance of international cooperation required to maintain station operations provides lessons that extend far beyond space exploration. Consider the complexity of coordinating activities when crew members speak different languages, come from different cultures, and represent nations that may have political disagreements on Earth. Yet aboard the station, these differences become strengths rather than obstacles, as diverse perspectives and expertise combine to solve problems and advance scientific understanding. Mission control centers around the world maintain constant communication with the station, creating a global network of support that operates around the clock. Houston manages American operations, while Moscow coordinates Russian activities. Munich oversees European experiments, while Montreal monitors robotic operations. This international chorus of voices provides guidance, support, and expertise to the crew members who rely on ground-based teams for everything from daily scheduling to emergency procedures. The robotic systems aboard the station represent another marvel of international engineering cooperation. Canada's contributions include sophisticated robotic arms that can move with precision, measured in millimeters while manipulating objects weighing several tons. These mechanical marvels perform tasks that would be dangerous or impossible for human crew members, from capturing visiting spacecraft to installing new equipment on the station's exterior. Japan's contributions include both robotic systems and unique experimental facilities that take advantage of microgravity conditions. The Japanese experiment module provides specialized research capabilities that complement the work performed in other laboratory modules, creating a comprehensive research environment that serves scientists from around the world. European contributions encompass both hardware and scientific expertise, with laboratory modules designed to support research in multiple disciplines simultaneously. The European Space Agency's involvement demonstrates how international partnerships can leverage the strengths of different nations to achieve goals that would be impossible for any single country to accomplish alone. The logistics of keeping 7 people alive and productive in space require careful planning and precise execution of supply missions. Regular cargo flights deliver everything from scientific equipment to personal items, food supplies to spare parts. These supply missions represent complex choreography of spacecraft launches, orbital rendezvous, and docking procedures that must be performed with extraordinary precision. The economic impact of the International Space Station extends far beyond the direct costs of construction and operation. Technologies developed for space applications frequently find uses in terrestrial applications, from medical devices to manufacturing processes, from communication systems to environmental monitoring equipment. This technology transfer effect multiplies the value of space investments by creating innovations that improve life on Earth. Educational outreach programs connect the station to classrooms around the world, inspiring students to pursue careers in science, technology, engineering, and mathematics. Crew members regularly participate in educational events, demonstrating scientific principles in microgravity and sharing their experiences with young people who may one day follow in their footsteps. These educational connections help ensure that future generations will continue humanity's journey of exploration and discovery. The challenges of maintaining human health during long-duration spaceflight continue to reveal new insights about human physiology and adaptation. Medical research aboard the station contributes to understanding how the human body responds to radiation exposure, altered gravity, and psychological stress. These findings have applications not only for future space missions, but also for treating medical conditions on Earth. Sleep research in microgravity provides insights into circadian rhythm disorders and sleep disturbances that affect millions of people on Earth. The artificial day-night cycles maintained aboard the station, combined with careful monitoring of crew sleep patterns, contribute to better understanding of how light exposure and activity schedules influence human rest and alertness. The station's unique environment allows researchers to study aging processes in ways that would be impossible on Earth. The accelerated bone loss and muscle deterioration experienced by astronauts in microgravity mimics aspects of aging that occur over years on Earth, but happen much more rapidly in space. Understanding these processes could lead to better treatments for age-related conditions and improved quality of life for elderly populations. Fire safety research conducted aboard the station has revealed how flames behave in microgravity, leading to better understanding of combustion processes and improved fire suppression techniques. The discovery that flames burn differently in space, forming spherical shapes rather than the familiar teardrop patterns seen on Earth, has implications for both spacecraft safety and terrestrial fire prevention strategies. The study of plant growth in microgravity contributes to both space exploration goals and agricultural applications on Earth. Learning how to grow food in space will be essential for long-duration missions to Mars and beyond, while understanding how plants adapt to altered gravity conditions could lead to improved crop yields and growing techniques for challenging environments on Earth. Materials processing experiments take advantage of the unique conditions aboard the station to create substances with properties that cannot be achieved in terrestrial laboratories. These space-manufactured materials often exhibit superior characteristics that could lead to advances in electronics, construction materials, and manufacturing processes. The station's role as a platform for testing new technologies extends beyond scientific experiments to include evaluation of systems and procedures that will be essential for future exploration missions. Everything from waste management systems to communication protocols undergoes thorough testing in the station environment before being considered for use on missions to more distant destinations. Radiation research aboard the station contributes to understanding how cosmic radiation affects both human health and electronic systems. This research is crucial for planning missions beyond Earth's protective magnetic field, where astronauts and equipment will be exposed to higher levels of dangerous radiation from cosmic sources and solar activity. The psychological support systems developed for station crews provide models for maintaining mental health during isolation and confinement. These techniques will be essential for crews on multi-year missions to Mars, where communication delays with Earth will make real-time psychological support impossible. As we continue our exploration of humanity's greatest achievement, we discover that every aspect of the International Space Station contributes to a larger story of human determination, ingenuity, and cooperation. From the smallest scientific experiment to the largest technological system, every element serves multiple purposes in advancing our understanding of science, improving life on Earth, and preparing for humanity's next giant leaps into the cosmos. The complexity of spacewalks reveals perhaps the most dramatic aspect of life aboard the International Space Station. Picture stepping outside your home, but instead of walking onto a porch or sidewalk, you're floating in the vacuum of space, where there's no air to breathe, no sound to hear, and temperatures that can swing from blistering hot to impossibly cold within moments. This is the reality that astronauts face when they venture outside the protective hull of the station to perform maintenance, install new equipment, or conduct repairs that cannot be accomplished from inside the pressurized modules. These extravehicular activities represent the pinnacle of human space operations, requiring months of preparation and training for procedures that may last only a few hours. Every spacewalk begins years before it actually occurs, with astronauts practicing in massive underwater pools that simulate the weightless environment of space. The Neutral Buoyancy Laboratory in Houston contains 6 million gallons of water and a full-scale replica of the station's exterior, allowing crew members to rehearse every movement, every tool operation, and every contingency they might encounter while floating in the void. The training is exhaustive and precise. Astronauts spend approximately 7 hours underwater for every hour they will eventually spend walking in space. They practice connecting electrical cables while wearing bulky gloves that make fine motor control challenging. They learn to remove and replace equipment using tools designed specifically for use in vacuum conditions. They rehearse emergency procedures for situations ranging from damaged spacesuits to unexpected equipment failures, all while learning to work within the constraints of pressure suits that serve as personal spacecraft. The spacesuits themselves represent marvels of life support engineering. Each extravehicular mobility unit weighs more than 280 pounds on Earth, but becomes weightless in space, transforming from a burdensome load into a sophisticated life support system that maintains perfect atmospheric conditions while protecting its wearer from the harsh environment beyond the station's walls. These suits must provide oxygen for breathing, remove carbon dioxide from exhaled air, maintain comfortable temperatures despite extreme external conditions, and protect against micrometeoroid impacts that could puncture the fabric. The psychological demands of spacewalks extend beyond the technical challenges of working in vacuum conditions. Imagine floating in an environment where the nearest solid ground is 250 miles below your feet, where Earth appears as a massive sphere rotating slowly beneath you, and where the only thing between you and the infinite vacuum of space is a thin layer of specialized fabric and metal. The mental fortitude required to remain calm and focused while performing precise technical work in such conditions demonstrates the extraordinary training and selection process that produces spacewalking astronauts. Communication during spacewalks creates its own unique challenges and experiences. Radio transmissions provide the only connection between spacewalking crew members and their colleagues inside the station, as well as mission controllers on Earth. The conversations that occur during these activities reveal the careful balance between technical precision and human emotion, as astronauts describe the breathtaking views while simultaneously focusing on complex mechanical tasks. The tools used during spacewalks must function perfectly in conditions that would destroy most earthly equipment. Lubricants freeze solid in the cold of space. Metal components can weld themselves together through cold welding when molecular surfaces contact each other in vacuum conditions. Electronic systems must operate reliably despite extreme temperature variations and radiation exposure that would quickly damage similar devices on Earth. Safety protocols for spacewalks involve multiple redundant systems and procedures designed to ensure that crew members can survive equipment failures and unexpected situations. Each astronaut is connected to the station by multiple tethers that prevent them from floating away into space. Their spacesuits contain emergency life support systems that can sustain them for hours if primary systems fail. Rescue procedures exist for scenarios where a spacewalking crew member becomes separated from the station or experiences suit malfunctions. The views experienced during spacewalks provide perspectives on Earth and space that few humans will ever witness firsthand. Astronauts describe looking down at continents passing beneath them while simultaneously seeing the star-filled darkness of space stretching infinitely in all directions. They witness lightning storms from above, observe the thin blue line of Earth's atmosphere that protects all life on our planet, and experience the profound silence of space, broken only by their own breathing and radio communications. The scientific instruments installed and maintained during spacewalks extend the station's research capabilities far beyond what could be accomplished within the pressurized modules. External platforms house experiments that must be exposed to the space environment, from materials science investigations that study how various substances behave when exposed to vacuum and radiation, to astronomical observations that require unobstructed views of deep space objects. The international cooperation required for spacewalk operations demonstrates the remarkable coordination needed to maintain station operations. Russian spacesuits differ from American designs, requiring different procedures and support systems. European and Japanese equipment may require specialized installation techniques. Yet crew members from different countries work together seamlessly, using common procedures and communication protocols that transcend national boundaries and language differences. The evolution of spacewalk procedures over the decades of station operation reveals continuous learning and improvement in techniques for working in space. Early spacewalks were tentative explorations of what was possible in the space environment. Modern extravehicular activities represent refined procedures developed through experience, with improved tools, better techniques, and enhanced safety measures that allow crew members to accomplish increasingly complex tasks outside the station. The physiological effects of spacewalks add another layer of challenge to these already demanding operations. Working in a spacesuit for several hours while performing physically demanding tasks creates fatigue that differs from earthly exertion. The suit's internal pressure must be lower than the station's cabin pressure to allow flexibility in the joints, requiring crew members to pre-breathe pure oxygen for hours before beginning their spacewalk to prevent decompression sickness. The photography and videography captured during spacewalks provide some of the most stunning visual documentation of human space activities. These images serve not only as records of technical accomplishments, but also as powerful reminders of humanity's presence in space and our ability to work in environments that seem utterly hostile to human life. The maintenance work performed during spacewalks keeps the station operational far beyond its originally planned lifespan. Components that were expected to function for specific periods often require replacement or refurbishment to extend the station's useful life. These maintenance activities demonstrate the importance of human presence in space for tasks that require judgment, adaptability, and problem-solving capabilities that robotic systems cannot yet match. The training facilities used to prepare astronauts for spacewalks represent significant investments in specialized equipment and expertise. Beyond the underwater training pools, virtual reality systems allow crew members to practice procedures in simulated space environments. Reduced gravity aircraft provide brief periods of weightlessness for training specific techniques. These diverse training methods combine to prepare astronauts for the unique challenges of working in the space environment. The documentation and analysis of spacewalk procedures contribute to the development of techniques for future space missions. Every tool use, every procedure modification, and every lesson learned during station spacewalks informs the planning for missions to the Moon, Mars, and beyond. The experience gained from hundreds of hours of extravehicular activity provides an irreplaceable foundation for human space exploration activities that will take place far from Earth. The emergency response capabilities developed for spacewalk operations extend to other aspects of station safety. The procedures, equipment, and training used to ensure spacewalker safety contribute to overall crew safety systems that protect against various types of emergencies that could occur aboard the station. The partnership between spacewalking crew members and robotic systems demonstrates the complementary nature of human and machine capabilities in space operations. Robotic arms position crew members and equipment with precision that would be difficult to achieve through human movement alone, while astronauts provide the dexterity and judgment needed for complex manipulation tasks that challenge current robotic capabilities. The psychological support provided to spacewalking astronauts includes preparation for the sensory experiences that accompany working in space. The vast scale of Earth visible below, the infinite darkness of space above, and the profound silence of the vacuum environment can create emotional responses that must be managed while maintaining focus on technical tasks. Training programs prepare crew members for these psychological aspects of spacewalk operations. The legacy of spacewalk operations aboard the International Space Station extends far beyond the specific tasks accomplished during each extravehicular activity. These operations demonstrate humanity's ability to work effectively in space, maintain complex systems in hostile environments, and adapt to challenges that could not be anticipated during initial design phases. This experience provides confidence that humans can successfully operate in space for the extended periods that will be required for missions to distant destinations. The technological innovations developed for spacewalk operations often find applications in terrestrial activities. Tools designed to function in vacuum conditions may prove useful for underwater operations or hazardous environment work on Earth. Life support systems developed for spacesuits contribute to the design of protective equipment for various industrial and emergency response applications. The international nature of spacewalk operations reflects the global character of the entire International Space Station program. Crew members from different countries work together outside the station, just as they collaborate inside, demonstrating that human cooperation can overcome the challenges of working in the most demanding environments imaginable. This cooperation provides a model for future international space exploration efforts that will require even greater levels of coordination and mutual dependence. The communication systems used during spacewalks must function reliably across multiple countries and agencies, creating protocols that ensure clear understanding despite potential language barriers and technical differences between various national systems. These communication procedures serve as models for the more complex coordination that will be required for international missions to other planets. The waste management and resource conservation practices developed for spacewalk operations contribute to the overall efficiency of station operations. Every tool, every component, and every supply item used during extravehicular activities must be carefully managed to minimize waste and maximize utility. These practices inform the development of sustainable space operations procedures that will be essential for long-duration missions, where resupply from Earth is impossible or impractical. As we continue exploring the remarkable achievement that is the International Space Station, the spacewalk operations reveal the extraordinary capability that emerges when human ingenuity, international cooperation, and technological innovation combine to overcome seemingly impossible challenges. These activities represent humanity at its best, working together to maintain and enhance our foothold in space while pushing the boundaries of what we can accomplish beyond the protective embrace of our home planet. The rhythm of daily operations aboard the station creates a unique culture that blends the precision of technical operations with the humanity needed to sustain psychological well-being during long periods of isolation and confinement. This culture has evolved over more than 2 decades of continuous habitation, incorporating lessons learned from early crews and adapting to the changing needs of an international community living and working in space. The choreography of daily life reveals how human beings adapt to an environment that challenges every assumption about how we live and work. Morning routines become exercises in 3-dimensional navigation as crew members float from their sleeping quarters to begin another day of extraordinary work in an extraordinary place. The simple act of brushing teeth requires specially formulated toothpaste that can be safely swallowed, since spitting in microgravity would create floating droplets that could interfere with equipment or be inhaled by other crew members. Personal hygiene takes on new dimensions when water doesn't flow downward, but instead forms perfect spheres that cling to surfaces through surface tension. Washing requires no-rinse shampoos and body wipes, while shaving must be done with special razors equipped with vacuum systems to capture whiskers before they float away and potentially clog air filters. These seemingly mundane activities require careful attention and modified techniques that crew members must master before they can focus on their primary scientific and maintenance responsibilities. The social dynamics of living in confined spaces with the same small group of people for months at a time create unique challenges that ground-based psychologists have studied extensively. Crew members come from different cultures, speak different languages, and bring different perspectives to their shared experience. Yet they must work together seamlessly, often in high-stress situations where miscommunication or personality conflicts could have serious consequences for mission success and crew safety. The selection process for station crew members considers not only technical competence and physical fitness, but also psychological resilience and interpersonal skills. Candidates undergo extensive evaluation to assess their ability to remain calm under pressure, work effectively in teams, and maintain positive relationships during extended periods of isolation. The most technically skilled individual may not be the best choice for a long-duration mission if they struggle with the social demands of confined living. Communication with Earth provides essential psychological support for crew members who may go months without seeing new faces or experiencing unscripted interactions with other people. Regular communication sessions with family members, friends, and colleagues help maintain emotional connections that are crucial for psychological well-being. These conversations often occur while crew members float near windows overlooking Earth, creating surreal juxtapositions between intimate personal discussions and the cosmic perspective of their orbital vantage point. The medical challenges of long-duration spaceflight extend far beyond the obvious effects of microgravity on bones and muscles. Crew members may experience changes in vision that can persist long after returning to Earth. The redistribution of bodily fluids in weightlessness can cause facial puffiness and congestion that makes crew members appear different from their earthbound appearances. Kidney stones become more likely due to bone calcium loss, while the risk of radiation exposure from cosmic rays and solar particles creates ongoing health concerns that must be carefully monitored. Emergency medical procedures aboard the station require specialized training and equipment designed for use in microgravity conditions. Performing cardiopulmonary resuscitation in weightlessness requires techniques that differ significantly from earthbound emergency medicine. Medical equipment must be secured to prevent it from floating away during critical procedures, while medications and supplies must be carefully organized and accessible in emergency situations. The psychological preparation for medical emergencies includes training for scenarios where crew members must treat colleagues who are also close friends and co-workers. The emotional stress of providing emergency medical care to someone you live and work with daily, while being hundreds of miles from the nearest hospital, requires mental preparation that goes beyond technical medical training. Crew members also serve as test subjects for medical research, participating in experiments that study how their own bodies adapt to the space environment. They collect biological samples, perform ultrasound examinations on themselves and their colleagues, and participate in exercise studies that require them to work to exhaustion while researchers monitor their physiological responses. This dual role as both researcher and research subject creates unique ethical and practical considerations for space medicine. The dietary challenges of space nutrition go beyond the obvious constraints of eating in microgravity. Maintaining proper nutrition becomes more complex when taste preferences change. Appetite may be reduced, and the variety of available foods is limited by storage constraints and shelf life requirements. Crew members often lose weight during their missions, despite careful meal planning and caloric calculations performed by nutritionists on the ground. The social aspects of shared meals take on heightened importance when crew members have limited opportunities for casual interaction. Meals become important social times when crew members can discuss their work, share personal stories, and maintain the human connections that are essential for psychological health. Some crew members describe these shared meals as among their most cherished memories from their time in space. Food preferences and cultural dietary requirements must be accommodated within the constraints of space food systems. Crew members from different countries bring different expectations about meals, flavors, and eating customs. Creating menu systems that satisfy diverse cultural preferences while meeting nutritional requirements and storage constraints requires careful planning and frequent menu modifications based on crew feedback. The preparation of special meals for holidays and celebrations demonstrates the importance of maintaining cultural traditions and marking significant events even in the isolated environment of space. These celebrations help crew members maintain connections to their earthbound lives while creating new traditions unique to their space-based community. The scientific work conducted aboard the station operates on timescales that range from minutes to years, creating complex scheduling challenges that must balance immediate operational needs with long-term research objectives. Some experiments require precise timing that must be coordinated with ground-based researchers, while others involve biological specimens that develop according to their own natural rhythms regardless of human schedules. The data collection and analysis procedures for space-based research involve sophisticated systems for capturing, storing, and transmitting information to researchers around the world. High-resolution cameras document experimental procedures and results, while specialized sensors monitor environmental conditions that might affect experimental outcomes. This data must be carefully managed and transmitted to Earth using communication systems that operate intermittently as the station orbits the planet. The collaboration between space-based crew members and ground-based researchers creates unique challenges for scientific communication. Researchers on Earth may have immediate questions about experimental procedures or unexpected results, but communication opportunities are limited to specific times when the station passes over ground stations. This delay in communication requires careful planning and clear procedures that allow experiments to continue even when direct consultation with ground-based experts is not possible. The educational outreach activities conducted by crew members demonstrate the inspirational power of human space exploration. Students around the world participate in educational events where they can ask questions directly to people living in space, creating memorable experiences that often inspire young people to pursue careers in science and engineering. These educational interactions require crew members to communicate complex scientific concepts in terms that students can understand, while also conveying the wonder and excitement of space exploration. The photography and videography performed by crew members serves both scientific and public outreach purposes. Earth observation photography contributes to climate research, disaster monitoring, and environmental studies, while also creating stunning visual records of our planet as seen from space. The techniques required for photography in microgravity differ from terrestrial photography, as cameras must be carefully controlled to prevent them from floating away, and lighting conditions change rapidly as the station moves between sunlight and shadow. The artistic and creative expressions of crew members provide insights into how human creativity adapts to the space environment. Some crew members write poetry or music inspired by their orbital perspective, while others create visual art that captures their unique experiences. These creative works contribute to our understanding of how human consciousness and creativity respond to the profound experience of seeing Earth from space. The maintenance of personal spaces within the station's cramped quarters becomes important for psychological well-being. Each crew member has a small private area that they can personalize with photos, personal items, and mementos from home. These spaces provide essential privacy and personal identity in an environment where most activities are shared and public. The adaptation to microgravity affects not only physical activities, but also cognitive functions and sensory perceptions. Crew members report changes in their sense of orientation and spatial relationships as they adapt to an environment where up and down have no meaning. These adaptations may affect problem-solving approaches and creative thinking in ways that researchers are still working to understand. The return to Earth presents its own set of challenges, as crew members must readapt to gravity's constant downward pull. Simple activities like walking, climbing stairs, and lifting objects become difficult after months of weightlessness. The psychological adjustment to returning to Earth includes adapting to the weight of their own bodies and the sensation of objects falling when released. The long-term health monitoring of crew members continues for months or years after their return to Earth, providing valuable data about the lasting effects of space habitation on human physiology. This research contributes to our understanding of how human beings might adapt to even longer missions that will be required for journeys to Mars and other distant destinations. The career impacts of serving aboard the station extend far beyond the immediate experience of living in space. Crew members often become advocates for space exploration, educators who share their experiences with students and the public, and researchers who continue working on space-related projects throughout their careers. Their unique perspectives inform policy decisions, educational programs, and future mission planning in ways that benefit the entire space exploration community. The technological innovations developed for station operations often find unexpected applications in terrestrial activities. Water purification systems designed for space use contribute to clean water technologies for remote communities on Earth. Exercise equipment developed for microgravity finds applications in rehabilitation medicine. Life support systems inform the design of equipment for extreme environments on Earth, from underwater habitats to remote research stations. The philosophical implications of permanent human habitation in space challenge traditional concepts of home, citizenship, and human identity. Crew members often describe experiencing a shift in perspective that transcends national boundaries and political differences, seeing Earth as a single, fragile planet rather than a collection of separate countries. This overview effect has influenced environmental awareness, international cooperation efforts, and concepts of global citizenship. The legacy of continuous human presence in space for more than 2 decades demonstrates that our species can adapt to environments far beyond those in which we evolved. This achievement provides confidence that human beings can successfully establish permanent settlements on other worlds, expanding our civilization beyond the confines of our home planet. The lessons learned from station operations inform the planning for lunar bases, Mars colonies, and eventually human expansion throughout the solar system. The International Space Station represents far more than a technological achievement or scientific laboratory. It embodies humanity's capacity to overcome seemingly impossible challenges through cooperation, perseverance, and shared commitment to advancing knowledge and expanding our presence in the universe. Every day that crew members continue living and working aboard this remarkable facility, they extend humanity's foothold in space while conducting research that benefits life on Earth and prepares us for our next giant leaps into the cosmos. As we prepare to explore even more fascinating aspects of this incredible achievement, remember that right now, as you contemplate these words, 7 remarkable human beings are floating 250 miles above your head, conducting experiments that could change the world, maintaining systems that keep them alive in the vacuum of space, and demonstrating every single day that when we work together, we can accomplish the extraordinary. The story of the International Space Station continues to unfold with new discoveries, new challenges, and new achievements that push the boundaries of human capability and scientific understanding. This remarkable facility serves as both our current home in space and our stepping stone to destinations we can barely imagine, proving that the greatest adventures in human history are not behind us, but waiting just beyond the next horizon. Tonight, as we drift deeper into the extraordinary story of humanity's greatest achievement, we encounter perhaps the most remarkable aspect of the International Space Station: its role as a bridge between worlds. Not just the physical bridge spanning the gap between Earth and space, but a bridge across time, connecting our present capabilities to future possibilities that stretch far beyond anything we've previously imagined. The station serves as our cosmic laboratory for testing technologies that will one day carry human beings to destinations that exist only in our dreams today. Every system aboard this remarkable facility, from the most complex life support mechanisms to the simplest tools used for maintenance, undergoes constant evaluation and refinement with future missions in mind. The water recycling systems that turn waste into drinking water cleaner than most municipal supplies on Earth represent early versions of the closed-loop life support systems that will sustain crews during multi-year journeys to Mars and beyond. Imagine the profound implications of this technological development. Future explorers venturing to the Red Planet will rely on lessons learned from decades of station operations, where crew members have demonstrated that human beings can thrive in completely artificial environments for extended periods. The psychological protocols developed through years of studying crew interactions in isolation will guide the selection and support of astronauts who will spend years traveling through the void between worlds, knowing that Earth appears as nothing more than a pale blue dot in their rear-view cameras. The medical knowledge gained from monitoring how human bodies adapt to prolonged weightlessness directly informs the development of countermeasures for the health challenges that will face interplanetary travelers. Every exercise session performed on the station's sophisticated equipment contributes to our understanding of how to maintain human health during journeys that may last several years. Every meal consumed in microgravity helps refine the nutritional strategies needed to sustain crews when fresh supplies from Earth become impossible. But the station's influence extends far beyond the practical challenges of space travel. The international cooperation required to maintain this facility has created new models for how different nations can work together on projects that benefit all humanity. When political tensions rise on Earth, the station continues operating smoothly overhead, with crew members from different countries working side by side, sharing meals, conducting experiments, and supporting each other through the challenges of life in space. This cooperation has survived changes in government, international crises, and global pandemics, demonstrating that shared scientific goals can transcend earthly divisions. The protocols developed for international coordination aboard the station provide templates for future collaborative missions that will require even greater levels of trust and interdependence. When human beings establish permanent settlements on other worlds, they will rely on cooperation models tested and refined through decades of station operations. The economic impacts of this remarkable facility ripple through industries and communities around the world in ways that often remain invisible to casual observers. The technologies developed for space applications frequently find their way into everyday life, improving everything from medical devices to manufacturing processes. Water purification systems designed to function in microgravity now provide clean drinking water in remote communities on Earth. Materials processing techniques developed for space manufacturing contribute to advances in electronics and construction materials. The commercial space industry that has emerged around station operations represents a fundamental shift in how humanity approaches space exploration. Private companies now regularly deliver cargo and crew to the station, reducing costs while increasing reliability and frequency of access to space. This commercialization of space transportation has opened new possibilities for research, manufacturing, and eventually tourism that were unimaginable when the station was first conceived. Commercial crew vehicles developed by private companies have transformed how astronauts travel to and from the station. These spacecraft incorporate lessons learned from decades of government-operated space transportation, while introducing innovations that improve safety, comfort, and efficiency. The success of these commercial systems demonstrates that space exploration can transition from purely government-funded activities to sustainable commercial enterprises that serve multiple customers and purposes. The research conducted aboard the station increasingly involves partnerships between government agencies, academic institutions, and private companies, creating new models for conducting science in space. Pharmaceutical companies use the microgravity environment to develop new medicines, while technology companies test equipment that may eventually serve both terrestrial and space-based applications. These partnerships leverage the unique capabilities of the space environment while sharing costs and risks among multiple organizations. The educational programs associated with the station have inspired an entire generation of students to pursue careers in science, technology, engineering, and mathematics. Students who participated in educational events with station crew members have gone on to become engineers, scientists, and astronauts themselves, creating a continuous cycle of inspiration and achievement that extends far beyond the station's immediate mission. Universities around the world have developed research programs that take advantage of the station's unique environment, giving students opportunities to design and conduct experiments in microgravity. These educational partnerships provide practical experience for future scientists and engineers, while advancing research objectives that benefit from the space environment. The cultural impact of continuous human presence in space has subtly influenced how our species thinks about its place in the universe. The photographs of Earth taken from the station have become iconic images that help people visualize our planet's fragility and beauty. The perspective gained by seeing Earth from space, with its thin atmosphere and lack of visible political boundaries, has influenced environmental movements, international cooperation efforts, and philosophical discussions about human identity. and responsibility. Crew members often describe their experience aboard the station as transformative, changing how they view both the cosmos and their role as human beings. This transformation doesn't end when they return to Earth, but continues influencing their careers, their advocacy for space exploration, and their efforts to share the profound perspective that comes from seeing our world from space. The station's role as a platform for astronomical observations has contributed to our understanding of the universe beyond our solar system. Free from atmospheric interference and light pollution, instruments aboard the station can observe cosmic phenomena with clarity impossible from Earth-based facilities. These observations contribute to research into dark matter, black holes, and the fundamental structure of space and time itself. The biological research conducted in the station's unique environment has revealed new insights into fundamental life processes that operate differently in the absence of gravity. Plants grow in unexpected ways when they cannot sense up from down, revealing new information about how living organisms orient themselves and allocate resources. These discoveries have applications for agriculture on Earth as well as for growing food during long-duration space missions. Protein crystallization experiments continue yielding results that contribute to drug development and medical research. The larger, more perfect crystals that form in microgravity provide detailed molecular structures that help researchers understand how diseases develop and how new treatments might be designed. Some of these space-grown crystals have contributed to the development of medicines currently helping patients on Earth. The study of aging processes in microgravity has provided insights that benefit elderly populations on Earth. The accelerated bone loss and muscle deterioration experienced by astronauts in space mimics aspects of aging that occur over years on Earth, but happen much more rapidly in the space environment. Understanding these processes helps develop better treatments for age-related conditions and improved quality of life for aging populations. Materials science experiments conducted aboard the station take advantage of the unique conditions of microgravity to create substances with properties that cannot be achieved in terrestrial laboratories. Metals can be combined in ways that gravity would prevent, creating alloys with superior strength or other desirable characteristics. These space-manufactured materials often exhibit properties that could revolutionize manufacturing and engineering applications. The combustion research performed in the station's laboratories has revealed phenomena that exist only in microgravity environments. Cool flames that burn at lower temperatures and produce different chemical reactions cannot be sustained on Earth because gravity causes hot gases to rise and disrupt the combustion process. Understanding these unique combustion processes could lead to more efficient engines and cleaner burning technologies for applications ranging from automotive engines to power generation systems. Fluid physics experiments in microgravity offer insights that improve everything from industrial processes to medical devices. Without gravity's influence on fluid behavior, researchers can observe how liquids behave based purely on surface tension, viscosity, and molecular forces. These observations lead to better understanding of fluid dynamics that has practical applications in designing more efficient systems for moving and processing liquids in various industries. The station serves as a unique platform for Earth observation and environmental monitoring. From their vantage point high above the planet's surface, crew members can observe weather patterns, natural disasters, and environmental changes with perspectives impossible to achieve from ground-based locations. This research contributes to climate science, disaster response planning, and environmental monitoring efforts that help protect and preserve our planet. The psychological research conducted through decades of station operations has provided valuable insights into human behavior during isolation, confinement, and high-stress situations. These findings have applications beyond space exploration, informing practices in fields ranging from submarine operations to Antarctic research stations, from long-term medical care facilities to emergency response planning. The communication systems developed for station operations have advanced technologies for maintaining reliable contact across vast distances under challenging conditions. These systems must function reliably when the station passes behind Earth relative to ground stations, when solar activity interferes with radio transmissions, and when equipment failures require backup communication methods. The lessons learned from maintaining constant communication with the station have applications for other remote operations and emergency communication systems. The life support systems aboard the station represent remarkable achievements in closed-loop environmental control. The ability to maintain breathable atmosphere, comfortable temperatures, and safe drinking water in a completely artificial environment demonstrates technologies that will be essential for permanent human settlements on other worlds. These systems continuously recycle air, water, and waste products with efficiency levels that exceed many terrestrial systems. The robotic systems that support station operations have advanced the field of remote manipulation and automated assistance. The robotic arms that can manipulate objects weighing several tons with precision measured in millimeters demonstrate capabilities that have applications in manufacturing, construction, and hazardous material handling on Earth. The techniques developed for human-robot collaboration in space inform the design of robotic assistants for various terrestrial applications. The logistics systems required to keep the station supplied and operational have advanced space transportation and cargo handling technologies. The precision required for spacecraft to rendezvous and dock with the station has applications for other space operations, from satellite servicing to asteroid mining. The cargo handling systems developed for transferring supplies in microgravity have influenced the design of automated material handling systems for various industries. The power generation and distribution systems aboard the station have advanced technologies for renewable energy and efficient electrical systems. The solar arrays that track the sun as the station orbits demonstrate advanced solar tracking technologies, while the power management systems that distribute electricity throughout the station's complex systems provide models for efficient electrical distribution in other applications. The thermal control systems that maintain comfortable temperatures throughout the station despite extreme external temperature variations have applications for building design and industrial process control. The techniques used to manage heat distribution in the space environment inform the development of more efficient heating and cooling systems for terrestrial applications. The waste management systems developed for station operations have advanced recycling and resource recovery technologies. The ability to process and recycle human waste, food waste, and other materials in a closed system provides models for sustainable waste management in remote locations and resource-constrained environments on Earth. The quality control and reliability engineering practices developed for station systems where failure could have life-threatening consequences have influenced standards and practices in various industries where safety and reliability are critical. The redundant systems and failure mitigation strategies employed aboard the station provide models for designing resilient systems in other applications. The training systems developed for preparing crew members for station operations have advanced simulation technologies and training methodologies. The virtual reality systems, underwater training facilities, and reduced gravity simulators used to prepare astronauts for space operations have applications for training in other high-risk, high-precision professions. The medical monitoring systems that track crew health aboard the station have advanced remote healthcare technologies. The ability to monitor vital signs, perform diagnostic procedures, and maintain health records for crew members in space has applications for providing medical care in remote locations on Earth, where access to healthcare facilities is limited. The food systems developed for station operations have advanced preservation technologies and nutrition science. The techniques used to package, store, and prepare nutritious meals for consumption in microgravity have applications for feeding people in challenging environments, from military operations to disaster relief efforts. The exercise equipment designed to function in microgravity has advanced rehabilitation medicine and fitness technologies. The devices that use vacuum cylinders and flywheel systems to provide resistance exercise in weightlessness have applications for physical therapy and fitness training in various contexts on Earth. As we continue exploring the remarkable legacy of the International Space Station, we begin to understand that its influence extends far beyond the immediate goals of scientific research and international cooperation. This facility represents humanity's first permanent foothold in space, demonstrating that our species can not only survive but thrive in environments completely unlike those in which we evolved. The lessons learned from more than 2 decades of continuous human habitation in space provide the foundation for all future human space exploration. Every challenge overcome, every system refined, and every procedure perfected aboard the station contributes to our species' growing capability to live and work beyond Earth. The knowledge gained from station operations will enable the establishment of permanent lunar bases, the first human missions to Mars, and eventually our expansion throughout the solar system. The technologies developed and tested aboard the station are already being incorporated into plans for future spacecraft and habitats. The life support systems, communication networks, and operational procedures that keep crew members safe and productive in space will form the backbone of humanity's next generation of space exploration vehicles and facilities. The international partnerships forged through station operations have created new models for cooperation that will be essential for future missions, requiring resources and expertise from multiple nations. The trust and coordination developed through decades of joint operations provide the foundation for even more ambitious cooperative ventures that will push humanity further into the cosmos. The scientific discoveries made possible by the station's unique environment continue advancing human knowledge across multiple disciplines. From fundamental physics to medical research, from materials science to biological studies, the research conducted in microgravity provides insights impossible to achieve through earthbound investigations alone. The inspiration generated by continuous human presence in space has motivated countless individuals to pursue careers in science, technology, engineering, and mathematics. The students who have participated in educational programs with station crew members represent the future generation of explorers who will carry humanity to new worlds and new discoveries. The economic innovations spawned by station operations have created new industries and business models that make space more accessible and affordable. The commercial space transportation systems developed to serve the station have reduced costs while increasing capabilities, opening space to new users and new applications. The cultural impact of seeing Earth from space, shared through the experiences of station crew members, has influenced how our species thinks about environmental protection, international cooperation, and our collective responsibility for preserving and protecting our home planet. As the station continues its mission, orbiting Earth every 90 minutes with 7 remarkable human beings aboard, it serves as both a symbol of human achievement and a stepping stone to even greater accomplishments that await us among the stars. The story of the International Space Station is far from over. Each day brings new discoveries, new challenges overcome, and new preparations for the next chapter in humanity's greatest adventure. The remarkable facility floating 250 miles above our heads represents not just what we have accomplished, but what we are capable of accomplishing when we work together towards shared goals that benefit all humanity. The International Space Station stands as proof that our greatest achievements lie not behind us, but ahead of us, waiting to be discovered in the infinite expanse of space that surrounds our small blue world. The delicate balance of human psychology in the confined environment of space reveals itself in ways that ground-based researchers could never fully anticipate. Picture 7. Individuals living together in a space smaller than a large house, where privacy consists of a telephone booth-sized crew quarters, and where the same faces greet you every morning for months on end. Yet somehow, these carefully selected individuals not only coexist peacefully, but form bonds that often last a lifetime. The selection process for station crew members extends far beyond technical competence and physical fitness. Candidates undergo extensive psychological evaluation that assesses their ability to maintain emotional stability under pressure, resolve conflicts constructively, and support their colleagues through the inevitable challenges of life in isolation. The most brilliant scientist or skilled pilot may not qualify for a long-duration mission if they struggle with the social demands of confined living, where there is literally nowhere to escape. Cultural adaptation takes on profound meaning when crew members from vastly different backgrounds must work together seamlessly. Imagine a Russian cosmonaut, an American astronaut, a Japanese engineer, and a European scientist sharing meals while discussing complex technical procedures, each bringing their own cultural perspectives to problem-solving and decision-making. The station has become a unique laboratory for studying how human cultures blend and adapt in extreme environments. Communication protocols aboard the station accommodate multiple languages and cultural communication styles. While English serves as the primary working language, crew members often switch between languages during informal conversations, creating a multicultural environment that reflects the station's international character. Mission control centers around the world coordinate their activities in multiple languages, with translators and cultural liaisons ensuring that critical information is clearly understood across all international partners. The daily rhythm of life aboard the station creates its own unique culture that has evolved over more than 2 decades of continuous habitation. Morning briefings bring the crew together to discuss the day's activities, share concerns, and coordinate complex procedures that may involve multiple crew members working simultaneously on different experiments. These briefings serve not only operational purposes, but also important social functions that maintain crew cohesion and morale. Evening wind-down periods provide essential transition time between the intense focus required for scientific work and the relaxation needed for quality sleep. Crew members often gather near the station's windows to watch Earth pass by below, sharing observations about weather patterns, city lights, or natural phenomena visible from their orbital vantage point. These moments of shared wonder help maintain the emotional connections that are crucial for psychological well-being during long-duration missions. The management of personal time becomes critically important when every minute of the workday is scheduled and monitored. Crew members receive small amounts of discretionary time that they can use for personal activities, from reading and music to photography and communication with family members. How individuals choose to use this precious personal time often reflects their coping strategies for dealing with the stresses of space life. Personal hygiene routines must be completely reimagined in an environment where water doesn't flow and objects don't fall. The simple act of washing hair requires specially formulated no-rinse shampoos and careful technique to prevent water droplets from floating into sensitive equipment. Dental care involves toothpaste that can be safely swallowed and techniques that prevent any particles from escaping into the cabin atmosphere. The sensory experience of living in space differs dramatically from Earthbound life in ways that affect both physical comfort and psychological adaptation. The constant background hum of life support systems replaces the familiar sounds of wind, traffic, and human activity that provide unconscious comfort on Earth. The absence of gravity eliminates the tactile feedback that helps us maintain spatial orientation, requiring crew members to consciously think about which way is up in situations where such concepts have no meaning. Sleep patterns require careful management when the station experiences 15 sunrises and sunsets each day. Crew members use eye masks and earplugs to block out the changing light conditions and mechanical sounds that could disrupt their rest. The sleeping quarters provide small private spaces where individuals can retreat from the constant presence of their colleagues and find the solitude essential for psychological restoration. Dreams in space often reflect the unique environment in which crew members live. Many astronauts report dreams of flying or floating, experiences that may represent their subconscious minds processing the reality of living in weightlessness. Others dream of earthbound activities like walking or swimming, perhaps reflecting their psychological longing for familiar gravitational experiences. The psychological support systems developed for station crews include regular consultations with ground-based psychologists who monitor crew mental health and provide counseling when needed. These sessions must be conducted via radio or video links, creating unique challenges for mental health professionals who cannot observe body language or create the intimate therapeutic environment typically associated with psychological counseling. Conflict resolution procedures recognize that disagreements between crew members can have serious consequences for mission success and crew safety. Training programs teach crew members techniques for addressing interpersonal issues constructively, while maintaining the professional relationships essential for effective teamwork. The confined environment makes it impossible to avoid difficult colleagues, requiring sophisticated social skills and emotional maturity. The celebration of holidays and special occasions takes on heightened importance when crew members are separated from family and friends during significant personal or cultural events. Ground teams work carefully to coordinate special communications, surprise messages, or small gifts that help crew members maintain connections to their earthbound lives. These celebrations often become cherished memories that crew members carry long after returning to Earth. Family support systems extend beyond the crew members themselves to include their spouses, children, and other loved ones who experience their own unique stresses while their family member lives in space. Ground support teams provide counseling and assistance to family members who must cope with separation anxiety, media attention, and the constant awareness that their loved one is living in one of the most dangerous environments accessible to human beings. The reintegration process, when crew members return to Earth, involves both physical and psychological adaptation. After months of weightlessness, the simple act of walking requires conscious effort as the body readjusts to gravity's downward pull. Psychological readjustment may take even longer as returning crew members process their extraordinary experiences and find ways to integrate their space-based perspectives with their earthbound lives. Career impacts of serving aboard the station extend far beyond the immediate experience of living in space. Crew members often become advocates for space exploration, educators who share their experiences with students and the public, and advisors who inform policy decisions about future space missions. Their unique perspectives influence everything from spacecraft design to crew training programs to international cooperation agreements. The medical challenges of long-duration spaceflight continue revealing new insights about human physiology and adaptation. Vision changes experienced by some crew members have led to intensive research into how microgravity affects the human visual system. These discoveries have applications not only for space medicine, but also for understanding and treating vision problems that affect people on Earth. Bone density loss in microgravity occurs at rates comparable to severe osteoporosis, providing researchers with opportunities to study bone metabolism under accelerated conditions. The countermeasures developed to maintain bone health during spaceflight contribute to treatments for osteoporosis and other bone diseases that affect millions of people worldwide. Cardiovascular changes in microgravity include alterations in blood flow patterns, heart function, and blood pressure regulation. The monitoring systems used to track these changes aboard the station have advanced remote cardiac monitoring technologies that benefit patients in remote locations or those requiring continuous cardiac surveillance. Immune system function changes in ways that researchers are still working to understand. Some crew members experience increased susceptibility to infections, while others show enhanced immune responses to certain challenges. These findings contribute to immunology research that has applications for treating immune system disorders and improving vaccine effectiveness. Radiation exposure from cosmic rays and solar particles creates ongoing health concerns that require continuous monitoring and protective measures. The research conducted on radiation effects during spaceflight contributes to radiation medicine, cancer treatment protocols, and protective strategies for people exposed to radiation in various occupational settings. Nutritional research aboard the station extends beyond the obvious challenges of eating in microgravity to include studies of how nutritional needs change during spaceflight. metabolic changes, altered absorption of nutrients, and different physical activity patterns all affect how the body processes food and maintains nutritional balance. Exercise physiology research takes advantage of the unique conditions aboard the station to study how muscles and cardiovascular systems adapt to altered gravitational environments. The sophisticated exercise equipment aboard the station provides researchers with precise data about human performance under conditions that cannot be replicated on Earth. Sleep research in the space environment contributes to understanding circadian rhythm disorders, insomnia, and other sleep disturbances that affect millions of people. The artificial day-night cycles maintained aboard the station, combined with detailed monitoring of crew sleep patterns, provide insights into how environmental factors influence sleep quality and duration. Cognitive function research examines how mental performance changes during long-duration spaceflight. Attention, memory, decision-making, and problem-solving abilities are carefully monitored to understand how the space environment affects brain function and to develop strategies for maintaining peak mental performance during extended missions. The station serves as a unique laboratory for studying how human beings adapt to completely artificial environments. Every aspect of life support, from air purification to water recycling to waste management, must function perfectly to maintain conditions suitable for human survival. The lessons learned from maintaining these systems inform the design of life support technologies for future space missions and isolated terrestrial facilities. Environmental monitoring systems aboard the station track air quality, temperature, humidity, and other factors that affect crew comfort and health. These monitoring technologies have applications for indoor air quality management in buildings, industrial facilities, and other enclosed spaces where environmental control is important for occupant health and productivity. Emergency response procedures developed for station operations address scenarios ranging from medical emergencies to equipment failures to loss of atmospheric pressure. These procedures and the training systems used to prepare crew members for emergencies have applications for other high-risk environments where rapid, effective response to dangerous situations is essential for survival. The communication systems that maintain constant contact between the station and ground control centers around the world demonstrate advanced technologies for reliable communication under challenging conditions. These systems must function when the station passes behind Earth relative to ground stations, when solar activity interferes with radio transmissions, and when equipment failures require backup communication methods. Data management systems aboard the station handle enormous amounts of information from scientific experiments, system monitoring, crew health tracking, and operational communications. The techniques developed for organizing, storing, and transmitting this data have applications for managing large data sets in research, healthcare, and business applications. Quality control procedures ensure that every system aboard the station functions reliably, despite the harsh environment of space and the impossibility of quick repairs or replacements. These quality assurance methods influence standards and practices in industries where reliability and safety are critical considerations. The procurement and logistics systems that keep the station supplied demonstrate advanced planning and coordination capabilities. Every item sent to the station must be carefully selected, tested, packaged, and scheduled for delivery through complex transportation networks that involve multiple countries and commercial providers. Training systems developed for preparing crew members include sophisticated simulators, virtual reality environments, and specialized facilities that replicate conditions aboard the station. These training technologies have applications for preparing people to work in other challenging or dangerous environments where thorough preparation is essential for success and safety. The documentation and knowledge management systems that preserve lessons learned from station operations ensure that valuable experience and expertise are not lost when crew members rotate or when key personnel retire. These knowledge preservation methods have applications for organizations that must maintain continuity of operations despite personnel changes. International cooperation agreements that govern station operations provide models for managing complex multinational projects where different countries contribute resources and expertise while maintaining their own national interests. These cooperation frameworks inform the development of international agreements for other large-scale collaborative projects. The research partnerships that connect the station to universities and research institutions around the world demonstrate new models for conducting science that leverages unique capabilities while sharing costs and expertise among multiple organizations. These partnership models influence how scientific research is organized and funded in other contexts. Technology transfer processes that move innovations from space applications to terrestrial uses have generated numerous commercial products and services that benefit people on Earth. These technology transfer mechanisms provide models for converting research investments into practical applications that create economic value and improve quality of life. Public outreach programs that connect station operations to schools and communities around the world demonstrate the inspirational power of human space exploration. These educational initiatives have influenced how scientific and technical organizations engage with the public to build support for their missions and inspire future generations of scientists and engineers. The International Space Station continues evolving as both a scientific laboratory and a model for human adaptation to extreme environments. Every day of operation provides new data, new insights, and new lessons that will inform humanity's next steps into the cosmos. The remarkable facility orbiting high above our heads represents not just a triumph of engineering and international cooperation, but a testament to our species' ability to adapt, survive, and thrive in environments that challenge every assumption about human limitations. As we drift toward the conclusion of our exploration tonight, remember that this extraordinary story is still being written. 7 remarkable human beings continue their work 250 miles above your head, pushing the boundaries of human knowledge and capability, while demonstrating that when we reach beyond our perceived limitations, we discover that the only true boundaries are those we impose upon ourselves. The International Space Station stands as proof that our greatest achievements happen not when we work alone, but when we combine our diverse strengths in pursuit of goals that benefit all humanity. The legacy of 25 years of continuous human habitation reveals itself in countless small moments that together form an extraordinary tapestry of human achievement. Picture the quiet morning routine of a crew member floating through the station's corridors, checking system displays that monitor the health of hundreds of components working in perfect harmony to maintain life in the vacuum of space. These routine tasks, performed thousands of times by hundreds of different people over more than 2 decades, represent the culmination of humanity's most ambitious engineering project. The accumulated wisdom gained from managing this complex facility has transformed our understanding of what human beings can accomplish when we commit to long-term collaboration across national boundaries and cultural differences. Every procedure refined, every problem solved, and every crisis overcome has contributed to a growing body of knowledge that will guide our species as we venture further into the cosmos. The evolution of the station itself tells a remarkable story of adaptation and growth. What began as a basic two-module structure has expanded into a sprawling complex that represents the pinnacle of human engineering achievement. Each new module added to the structure brought enhanced capabilities, expanded research opportunities, and improved living conditions for the brave souls who call this place home. The continuous process of upgrade and improvement demonstrates humanity's commitment to maintaining this outpost not just as a temporary experiment, but as a permanent foothold in space. Systems that were cutting-edge technology when first installed have been replaced with more advanced versions. Research facilities have been enhanced with new capabilities. Living spaces have been improved to better support crew comfort and psychological well-being during extended missions. The international nature of these improvements reflects the collaborative spirit that has defined the station from its earliest conception. When one partner develops a new technology or identifies an improvement opportunity, the benefits are shared among all participants. This cooperative approach to innovation has accelerated technological development while ensuring that all contributing nations benefit from advances made by their partners. The research conducted aboard the station has evolved from basic studies of how human beings adapt to weightlessness to sophisticated investigations that push the boundaries of multiple scientific disciplines simultaneously. Early experiments focused on fundamental questions about life in microgravity. Modern research addresses complex problems in medicine, physics, biology, and materials science that require the unique conditions available only in the space environment. The sophistication of current research programs reflects decades of learning how to conduct science effectively in microgravity conditions. Researchers have developed specialized techniques for handling samples, controlling variables, and documenting results in an environment where traditional laboratory methods don't apply. These methodological innovations have created new approaches to scientific investigation that benefit research conducted both in space and on Earth. The data collected from thousands of experiments has created an invaluable repository of scientific knowledge that continues growing with each passing day. This accumulated database represents one of the most comprehensive collections of information about how physical, biological, and chemical processes behave in the absence of gravity. Future researchers will mine this data for insights and discoveries for decades to come. The technological innovations developed for station operations have found their way into countless terrestrial applications, often in ways that the original designers never anticipated. Water purification systems designed to function in microgravity now provide clean drinking water in remote locations on Earth. Exercise equipment created for weightless environments has influenced rehabilitation medicine and fitness technology. Life support systems developed for space have informed the design of equipment for extreme environments, ranging from underwater habitats to Antarctic research stations. The economic impact of these technological spillovers extends far beyond the direct costs of station operations. Industries have been created around technologies originally developed for space applications. Jobs have been generated in communities around the world where space-related manufacturing and research facilities operate. Educational institutions have developed programs to train the workforce needed to support expanding space-related industries. The inspiration generated by continuous human presence in space has motivated countless individuals to pursue careers in science, technology, engineering, and mathematics. Students who participated in educational programs with station crew members have gone on to become engineers, scientists, doctors, and teachers themselves. This multiplier effect ensures that the station's influence on human development extends far beyond its immediate scientific and technological contributions. The cultural impact of seeing Earth from space, shared through the experiences and photographs of station crew members, has subtly influenced how our species thinks about environmental protection, international cooperation, and our collective responsibility for preserving our home planet. The perspective gained from viewing Earth as a single fragile oasis in the cosmic darkness has informed environmental movements, influenced policy decisions, and shaped public discourse about global challenges that require cooperative solutions. The philosophical implications of permanent human habitation beyond Earth challenge traditional concepts of home, citizenship, and human identity. Crew members often describe experiencing a profound shift in perspective that transcends national boundaries and political differences. This transformation in consciousness, multiplied across hundreds of individuals from dozens of countries, has created a growing community of people who see themselves as citizens of Earth rather than representatives of particular nations. The medical knowledge gained from monitoring human adaptation to long-duration spaceflight has contributed to advances in treating conditions that affect millions of people on Earth. Understanding how bones lose density in microgravity has informed treatments for osteoporosis. Research into muscle atrophy in weightlessness has contributed to rehabilitation medicine and treatments for muscular dystrophy. Studies of cardiovascular changes during spaceflight have advanced cardiac medicine and treatment protocols. The psychological research conducted through decades of studying crew interactions in isolation has provided insights that benefit people facing challenging situations on Earth. The techniques developed for maintaining mental health during confinement have applications for submarine crews, Antarctic researchers, hospital patients in long-term care, and individuals dealing with social isolation. The conflict resolution strategies developed for space crews have been adapted for use in various terrestrial settings, where people must work together effectively under stress. The life support technologies that maintain breathable atmosphere and clean water aboard the station have advanced environmental engineering in ways that benefit communities worldwide. The efficiency achieved in recycling air and water in space has informed the design of sustainable building systems and environmental management technologies. The techniques used to monitor and control air quality aboard the station have applications for improving indoor environments in schools, hospitals, and office buildings. The communication systems that maintain constant contact between the station and ground control centers have advanced technologies for reliable communication under challenging conditions. These systems must function when the station passes behind Earth relative to ground stations, when solar activity interferes with radio transmissions, and when equipment failures require backup communication methods. The lessons learned from maintaining reliable communication with the station have applications for emergency communication systems, remote facility monitoring, and mobile communication networks. The precision required for spacecraft to rendezvous and dock with the station has advanced automated navigation and control technologies. The techniques developed for approaching and connecting with a structure traveling at thousands of miles per hour have applications for autonomous vehicles, robotic systems, and precision manufacturing equipment. The sensors and control systems used for spacecraft docking have influenced the development of automated systems for various industrial and transportation applications. The power generation and distribution systems aboard the station have demonstrated advanced renewable energy technologies and efficient electrical systems. The solar arrays that track the sun as the station orbits have informed the development of solar tracking systems for terrestrial solar power installations. The power management systems that distribute electricity throughout the station's complex systems provide models for smart grid technologies and efficient electrical distribution networks. The materials and construction techniques developed for station assembly have influenced construction methods and materials science in numerous applications. The precision required for assembling complex structures in the harsh environment of space has informed the development of construction techniques for challenging terrestrial environments. The materials used in station construction have found applications in industries requiring lightweight, durable components that can withstand extreme conditions. The logistics and supply chain management systems that keep the station operational have advanced techniques for managing complex, time-critical deliveries across vast distances. The coordination required to deliver supplies to a constantly moving target in space has applications for managing supply chains in remote locations, disaster response scenarios, and time-sensitive delivery operations. The quality control and reliability engineering practices developed for station systems have influenced standards and practices in industries where failure could have serious consequences. The redundant systems and failure mitigation strategies employed aboard the station provide models for designing resilient systems in healthcare, transportation, energy generation, and other critical infrastructure applications. The training systems used to prepare crew members for station operations have advanced simulation technologies and training methodologies. Virtual reality systems developed for astronaut training have found applications in medical education, industrial training, and emergency response preparation. The techniques used to train people for working in challenging environments have been adapted for various high-risk professions. The international cooperation agreements that govern station operations provide models for managing complex multinational projects where different countries contribute resources while maintaining their own interests. These frameworks have influenced the development of international agreements for climate research, disaster response, and other global challenges that require coordinated action across national boundaries. The research partnerships that connect the station to institutions worldwide demonstrate new models for conducting science that leverages unique capabilities while sharing costs among multiple organizations. These collaborative approaches have influenced how scientific research is organized and funded in other contexts, creating more efficient and effective ways to address complex research challenges. The public outreach programs that connect station operations to schools and communities have demonstrated the power of human space exploration to inspire and educate. These programs have influenced how scientific organizations engage with the public to build support for their missions and inspire future generations of scientists and engineers. The economic development generated by space-related industries has created jobs and opportunities in communities around the world. Manufacturing facilities that produce components for the station and its supply missions have become economic anchors for their regions. Research institutions that conduct space-related studies have attracted talented scientists and engineers who contribute to local innovation ecosystems. The technological capabilities developed through station operations have positioned participating nations as leaders in high-technology industries that extend far beyond space applications. The expertise gained in life support systems, precision manufacturing, advanced materials, and complex system integration has applications across multiple industries and has enhanced the competitive positions of companies and countries that participated in station development. The safety systems and procedures developed for station operations have influenced safety practices in various industries where workers face hazardous conditions. The techniques used to ensure crew safety during spacewalks have applications for workers in construction, mining, underwater operations, and other environments where safety is paramount. The environmental monitoring systems that track conditions aboard the station have advanced technologies for monitoring air quality, water purity, and environmental conditions in various terrestrial applications. These monitoring systems have applications for ensuring safe conditions in buildings, industrial facilities, and environmental monitoring networks. The waste management and recycling systems developed for station operations have demonstrated advanced techniques for resource recovery and waste minimization. These systems have applications for sustainable waste management in remote locations and resource-constrained environments where traditional waste disposal methods are not feasible. The food systems that provide nutrition for station crews have advanced food preservation technologies and nutritional science. The techniques developed for packaging, storing, and preparing nutritious meals for consumption in challenging environments have applications for military operations, disaster relief efforts, and providing nutrition in remote locations. The exercise and health maintenance systems developed for use in microgravity have advanced rehabilitation medicine and fitness technologies. The equipment that provides resistance exercise in weightlessness has applications for physical therapy and fitness training in various contexts where traditional exercise equipment may not be suitable. The scientific instruments and experimental facilities aboard the station represent some of the most advanced research equipment ever deployed. These systems have pushed the boundaries of what's possible in terms of precision measurement, environmental control, and automated experimental procedures. The technologies developed for conducting research in the challenging environment of space have found applications in terrestrial research facilities where precise control of experimental conditions is essential. The data management systems that handle the enormous amounts of information generated by station operations have advanced techniques for organizing, storing, and analyzing large data sets. These systems must track everything from crew health data to experimental results to system performance metrics. The methods developed for managing this complex information have applications in research, healthcare, business analytics, and other fields where large amounts of data must be processed and analyzed. The human factors research conducted through decades of station operations has provided insights into how people perform complex tasks under stress, how teams function effectively in challenging environments, and how individuals maintain psychological well-being during extended isolation. These findings have applications for designing work environments, managing teams, and supporting individual performance in various demanding professions. The International Space Station stands as humanity's greatest achievement, not just because of its technological sophistication or scientific contributions, but because it represents our species' capacity to overcome seemingly impossible challenges through sustained collaboration, innovation, and commitment to goals that transcend individual interests. Every day that this remarkable facility continues operating, it extends our understanding of what human beings can accomplish when we work together toward shared objectives. The lessons learned from building, maintaining, and operating this complex facility provide the foundation for humanity's next steps into the cosmos. The technologies developed, the procedures refined, and the experience gained from decades of station operations will enable the establishment of permanent bases on the Moon, the first human missions to Mars, and eventually our expansion throughout the solar system. The international partnerships forged through station operations have created new models for cooperation that will be essential for future missions requiring resources and expertise from multiple nations. The trust and coordination developed through years of joint operations provide templates for even more ambitious collaborative ventures that will push humanity further into space. The scientific discoveries made possible by the station's unique environment continue advancing human knowledge in ways that benefit life on Earth, while preparing us for the challenges of living and working on other worlds. From medical breakthroughs to materials, innovations to fundamental physics discoveries, the research conducted in microgravity provides insights impossible to achieve through earthbound investigations alone. The inspiration generated by continuous human presence in space has motivated countless individuals to pursue careers in science and technology, while fostering a sense of global citizenship that transcends national boundaries. The perspective gained from seeing Earth from space has influenced environmental awareness, international cooperation efforts, and our collective understanding of humanity's place in the universe. The technological innovations spawned by station operations have created new industries and capabilities that make space more accessible while generating economic benefits that extend far beyond the direct costs of the program. The commercial space transportation systems developed to serve the station have reduced costs while increasing capabilities, opening space to new users and new applications that were unimaginable when the station was first conceived. As the station continues its mission, orbiting Earth every 90 minutes with 7 remarkable human beings aboard, it serves as both a symbol of human achievement and a stepping stone to destinations that exist only in our dreams today. The daily routine of scientific research, system maintenance, and international cooperation taking place 250 miles above our heads demonstrates that when we commit to working together toward shared goals, we can accomplish extraordinary things. The story of the International Space Station is far from over. Each day brings new discoveries, new challenges overcome, and new preparations for humanity's next chapter in space exploration. This remarkable facility has served as our training ground for learning to live and work beyond Earth, our laboratory for conducting research impossible to replicate on our home planet, and our symbol of what becomes possible when nations choose cooperation over competition. As you drift towards sleep tonight, remember that this extraordinary achievement continues unfolding above your head. 7 people are conducting experiments that could change the world, maintaining systems that demonstrate human ingenuity at its finest, and proving every single day that our greatest adventures lie not behind us, but ahead of us, waiting to be discovered among the stars. The International Space Station represents not just what we have accomplished, but what we are capable of accomplishing when we dare to reach beyond the boundaries of what seems possible and work together toward goals that benefit all humanity. The gentle hum of life support systems, the soft glow of instrument panels, and the breathtaking view of Earth passing by the windows create an environment unlike anywhere else in the universe. In this remarkable place where human beings have chosen to make their temporary home, the boundaries between nations fade away, replaced by the shared recognition that we are all travelers together on a small blue planet suspended in the cosmic darkness. And as these brave explorers continue their work, they carry with them the hopes and dreams of everyone who has ever looked up at the night sky and wondered what lies beyond the next horizon. The extraordinary nature of scientific discovery aboard the International Space Station reveals itself in ways that challenge our fundamental understanding of life itself. Tonight, as we float deeper into this cosmic story, we encounter research that transforms how we perceive the very building blocks of existence. Imagine proteins, those complex molecular machines that drive every process in your body, behaving completely differently when freed from gravity's constant downward pull. In the weightless environment of the station, these microscopic architects of life assemble themselves into structures of unprecedented clarity and perfection. On Earth, gravity creates currents and disturbances that interfere with protein formation, like trying to build a delicate house of cards during an earthquake. But in microgravity, proteins can grow into crystals so perfect, so precisely organized, that scientists can see molecular details invisible in any earthbound laboratory. These space-grown protein crystals are revolutionizing medicine in ways that touch millions of lives. Researchers studying cancer, Alzheimer's disease, Parkinson's, and heart conditions now have molecular blueprints of extraordinary detail that reveal exactly how these diseases develop and how new treatments might be designed. Some medications currently helping patients around the world exist because of protein research conducted in the silent laboratories floating above our heads. But the medical revelations extend far beyond protein crystallization. Stem cells, those remarkable cellular blank slates that can transform into any type of tissue, behave in fascinating ways when removed from gravity's influence. In space, they grow in greater quantities and with characteristics that differ dramatically from their Earth-grown counterparts. These space-cultivated cells show enhanced potential for regenerative therapies that could treat neurological damage, heart disease, and immune system disorders. The implications ripple through medicine like waves spreading across a still pond. Paralyzed patients might one day walk again, using therapies developed from stem cells grown in microgravity. Hearts damaged by disease could be repaired using techniques perfected in the weightless laboratories orbiting overhead. The cellular mysteries that have puzzled medical researchers for generations are slowly yielding their secrets to investigations conducted where gravity cannot interfere with fundamental biological processes. Fire itself behaves like a living entity when freed from Earth's gravitational constraints. In the station's combustion research facilities, flames take on shapes that would be impossible in any terrestrial laboratory. Instead of the familiar teardrop patterns we see on Earth, fires in microgravity form perfect spheres, burning at lower temperatures while producing completely different chemical reactions. These cool flames, as researchers call them, cannot exist on Earth because gravity causes hot gases to rise and disrupts the delicate combustion process. But in space, they burn steadily and quietly, revealing combustion secrets that could revolutionize engine design and energy production. The insights gained from studying these otherworldly flames are already influencing the development of more efficient automotive engines, cleaner industrial processes, and advanced rocket propulsion systems. The behavior of liquids in microgravity opens windows into fluid dynamics that transform our understanding of how matter moves and flows. Without gravity's downward pull, liquids form perfect spheres and behave according to forces that are often overwhelmed by gravitational effects on Earth. Surface tension, viscosity, and molecular attractions become the dominant influences, creating fluid behaviors that seem almost magical to those accustomed to earthbound physics. These fluid physics discoveries have practical applications that extend far beyond academic curiosity. Engineers designing more efficient fuel injection systems, medical device manufacturers developing better drug delivery mechanisms, and industrial process designers creating improved mixing and separation systems all benefit from research conducted in the station's unique environment. The study of materials in microgravity has revealed possibilities for creating substances with properties that cannot be achieved through any earthbound manufacturing process. When metals are melted and allowed to solidify in weightlessness, they form structures without the settling and segregation effects caused by gravity. Heavy elements don't sink to the bottom, while lighter materials float to the top. Instead, alloys form with uniform composition and enhanced properties that could revolutionize manufacturing and engineering applications. Advanced alloys created in space exhibit superior strength, improved electrical conductivity, or other desirable characteristics that make them valuable for applications ranging from aerospace engineering to electronic device manufacturing. These space-processed materials represent the early stages of what may eventually become entire industries based on manufacturing processes that can only be performed in microgravity environments. The station serves as humanity's most sophisticated Earth observation platform, providing perspectives on our planet that are impossible to achieve from any ground-based location. From their vantage point, high above the atmosphere, crew members can observe weather patterns developing across entire continents, track the movement of storms as they grow and evolve, and document environmental changes that occur over timescales ranging from days to decades. Climate researchers rely on data collected from the station to understand how Earth's atmosphere and oceans interact, how weather systems develop and move, and how human activities affect global environmental patterns. The long-term perspective provided by more than 2 decades of continuous observation has created an invaluable record of how our planet's climate system has changed over time. Natural disaster monitoring from space provides early warning capabilities that save lives and property around the world. Crew members can observe the development of hurricanes, track the progress of wildfires, and document the extent of flooding or other natural disasters with detail and timeliness that ground-based observers cannot match. This information helps emergency response teams prepare for disasters and coordinate relief efforts more effectively. The psychological research conducted aboard the station provides insights into human behavior that have applications far beyond space exploration. Living in isolation and confinement while performing demanding work under constant scrutiny requires mental resilience and coping strategies that benefit people facing challenging situations on Earth. The techniques developed for maintaining crew mental health during long-duration missions inform treatment approaches for depression, anxiety, and other psychological conditions. Social dynamics research conducted through decades of multicultural crew operations has revealed how people from different backgrounds can work together effectively despite language barriers, cultural differences, and conflicting perspectives. These findings influence team-building strategies, conflict resolution techniques, and intercultural communication methods used in businesses, educational institutions, and international organizations. The station's role as a testing ground for technologies that will enable future deep space missions cannot be overstated. Every system aboard this remarkable facility undergoes continuous evaluation and refinement with an eye toward missions that will take human beings to the Moon, Mars, and eventually other star systems. The life support systems that recycle air and water with remarkable efficiency will form the foundation of spacecraft that must sustain crews for years during journeys to distant worlds. Navigation and guidance systems tested aboard the station contribute to the development of spacecraft that must operate autonomously during missions where communication delays with Earth make real-time control impossible. The techniques developed for maintaining and repairing complex systems in the harsh environment of space inform the design of equipment that must function reliably during multi-year missions, where replacement parts cannot be obtained from Earth. Robotic systems that assist with station operations and maintenance demonstrate capabilities that will be essential for future exploration missions. The robotic arms that manipulate multi-ton objects with millimeter precision show how human crews and automated systems can work together to accomplish tasks that neither could perform alone. These human-robot partnerships will be crucial for establishing permanent bases on other worlds, where human crews must work alongside sophisticated robotic assistants. The communication technologies that maintain constant contact between the station and ground control centers are being refined and enhanced for missions that will venture far beyond Earth's orbit. As spacecraft travel to Mars and other distant destinations, communication delays will stretch from seconds to many minutes, requiring new protocols and procedures that allow crews to operate autonomously while maintaining contact with mission controllers on Earth. Power generation and management systems aboard the station demonstrate renewable energy technologies that will be essential for permanent settlements on other worlds. The solar arrays that track the Sun as the station orbits provide models for solar power systems that could operate on the Moon or Mars. Energy storage and distribution systems developed for station operations inform the design of power grids for lunar bases and Martian colonies. Resource utilization technologies developed for station operations point toward the capability to extract and process materials found on other worlds. Water recycling systems that achieve remarkable efficiency in space could be adapted for processing water ice found on the Moon or Mars. Atmospheric processing systems that maintain breathable air aboard the station could be modified to extract oxygen from the carbon dioxide-rich atmosphere of Mars. Waste management and recycling systems demonstrate closed-loop resource utilization that will be essential when resupply from Earth becomes impossible or prohibitively expensive. The techniques developed for processing and reusing every possible material aboard the station provide models for sustainable living that could support permanent human settlements throughout the solar system. Food production research conducted in the station's plant growth facilities explores how crops might be cultivated during long-duration missions or in permanent settlements on other worlds. Learning to grow nutritious food in controlled environments without soil, with carefully managed atmospheric conditions and under artificial lighting, provides essential knowledge for feeding crews during multi-year missions to Mars and beyond. The educational impact of the station extends far beyond inspiring individual students to pursue careers in science and technology. Entire educational systems have been transformed by programs that connect classrooms to space-based research and operations. Students who participate in these programs don't just learn about science. They experience firsthand how scientific research is conducted and how international cooperation makes extraordinary achievements possible. Universities around the world have developed research programs that take advantage of the station's unique capabilities, providing graduate students and faculty members with opportunities to conduct experiments that would be impossible in any terrestrial laboratory. These academic partnerships create pathways for the next generation of researchers to contribute to space-based science while advancing their own careers and education. The technological innovations that emerge from station operations often find unexpected applications in fields that seem completely unrelated to space exploration. Medical devices incorporate sensors and control systems originally developed for monitoring crew health in space. Manufacturing processes use techniques developed for assembling complex structures in challenging environments. Communication systems employ protocols designed for maintaining reliable contact across vast distances under difficult conditions. Economic development in communities around the world has been stimulated by industries that grew up around station operations. Manufacturing facilities that produce components for the station and its supply missions have become significant employers and economic drivers. Research institutions conducting space-related studies have attracted talented scientists and engineers who contribute to local innovation ecosystems that benefit entire regions. The commercial space industry that has emerged around station operations represents a fundamental shift in how space exploration and utilization are conducted. Private companies now routinely deliver cargo and crews to the station, reducing costs while increasing the frequency of access to space. This commercialization has opened new possibilities for research, manufacturing, and eventually tourism that were unimaginable when the station was first conceived. Space tourism may seem like a luxury for the wealthy, but the technologies and procedures being developed for commercial space flights have applications that could make space more accessible to researchers, educators, and others whose work could benefit from access to the microgravity environment. As costs continue to decrease and safety systems improve, the station may eventually serve as a destination for visitors who come not just for the experience, but to conduct specific research or educational activities. Manufacturing in space represents a potential industry that could produce materials and products with properties impossible to achieve on Earth. The microgravity environment allows for manufacturing processes that create superior alloys, perfect crystals, and other materials with applications ranging from electronics to construction to medical devices. As launch costs decrease and return capabilities improve, space-based manufacturing could become economically viable for high-value products. The International Cooperation Framework that governs station operations provides a model for managing complex projects that require contributions from multiple countries while respecting national interests and capabilities. This framework has survived changes in government, international tensions, and global crises, demonstrating that shared scientific and exploration goals can transcend political differences and create lasting partnerships. Future international missions to the Moon, Mars, and other destinations will require even greater levels of cooperation and coordination than station operations demand. The trust, communication protocols, and management structures developed through decades of station operations provide templates for organizing these more ambitious collaborative ventures that will push humanity deeper into the solar system. The cultural exchange that occurs aboard the station creates understanding and friendship among people from different countries and backgrounds. Crew members often describe their space experiences as transformative, changing how they view not only the cosmos, but also their relationships with colleagues from other nations. These personal connections between individuals who represent their countries in space contribute to international goodwill and cooperation that extends far beyond space exploration. The perspective gained from seeing Earth from space, often called the overview effect, has influenced environmental awareness and global citizenship among crew members and those who view their photographs and hear their descriptions of our planet. The vision of Earth as a single fragile oasis suspended in the cosmic darkness has motivated environmental protection efforts, international cooperation initiatives, and philosophical discussions about humanity's place in the universe. Religious and spiritual perspectives have been enriched by the experiences of crew members who have contemplated their relationship with the divine while floating in space. Representatives of various faith traditions have found their spiritual beliefs deepened rather than challenged by their cosmic perspective. These experiences contribute to interfaith dialogue and understanding about how scientific discovery and spiritual belief can complement rather than conflict with each other. Artistic expression inspired by space experiences has produced literature, music, visual art, and other creative works that help communicate the wonder and significance of human space exploration to broader audiences. Crew members, who are also artists, have created works that capture perspectives and emotions that can only be experienced firsthand in space, sharing these unique viewpoints with people who may never have the opportunity to leave Earth themselves. The documentation and preservation of station operations create historical records that will inform future generations about this remarkable period in human history. Every procedure, every experiment, every challenge overcome, and every discovery made is carefully recorded for analysis and reference by future researchers, engineers, and mission planners. This accumulated knowledge represents an invaluable resource for planning and conducting future space exploration missions. Archive systems that preserve decades of operational data, experimental results, crew observations, and technical documentation ensure that lessons learned from station operations will not be lost as personnel change and technologies evolve. These archives serve as libraries of human space exploration knowledge that will guide decision-making for generations to come. The legacy planning for station operations includes preparations for the eventual end of the facility's operational life and the transition to new space-based platforms that will continue and expand upon the work begun aboard the station. The knowledge, experience, and capabilities developed through station operations will transfer to new facilities and missions that will carry human space exploration forward into the future. As the International Space Station continues its silent journey around our planet, carrying 7 remarkable human beings who represent the best of our species' spirit of exploration and discovery, it serves as both a symbol of what we have accomplished and a stepping stone to achievements that we can barely imagine. Every orbit completed, every experiment conducted, and every challenge overcome adds another page to the most extraordinary chapter in human history. The quiet revolution happening 250 miles above your head continues transforming our understanding of medicine, materials, physics, and biology, while preparing our species for journeys that will take us far beyond the protective embrace of our home world. In the gentle hum of life support systems and the soft glow of instrument panels, human ingenuity and international cooperation have created something magnificent that points toward a future among the stars. Tonight, as you prepare to drift into sleep, remember that this remarkable story is still being written by people who chose to leave Earth behind temporarily, so that all of humanity might one day call the cosmos home. The International Space Station stands as proof that when we reach beyond what seems possible and work together toward goals that benefit everyone, we discover that our greatest adventures are not behind us, but ahead of us, waiting to unfold in the infinite expanse of space and time. The quiet moments between scheduled activities aboard the station reveal perhaps the most profound aspect of human adaptation to life beyond Earth. Picture a crew member floating near one of the station's windows during a rare break in their carefully orchestrated schedule, watching the Terminator line sweep across continents as day becomes night in the span of minutes. In these contemplative interludes, separated from everything familiar by 250 miles of vacuum, human consciousness encounters perspectives that fundamentally alter how we understand our place in existence. The sensory deprivation that defines life in space creates an almost meditative environment where the constant background noise of Earth-based living falls away, replaced by the gentle hum of fans and the subtle vibrations of machinery that keep 7 people alive in an environment that would kill them in seconds without technological intervention. This sonic landscape of survival becomes the soundtrack for discoveries that reshape our understanding of fundamental physical processes. Consider the extraordinary research being conducted in the realm of fundamental physics, where the absence of gravity allows scientists to observe phenomena that remain hidden in Earth-based laboratories. The creation of Bose-Einstein condensates, exotic states of matter that exist only at temperatures approaching absolute zero, becomes possible in ways that terrestrial facilities cannot achieve. These quantum mechanical entities behave according to rules that seem to violate common sense, existing simultaneously in multiple states until observed, demonstrating the strange reality that underlies everything we think we understand about the nature of matter and energy. The study of these quantum systems in microgravity provides insights that could revolutionize computing, communications, and energy production in ways that stretch the boundaries of current imagination. Quantum computers that harness these bizarre properties might one day solve problems that would take conventional computers longer than the age of the universe to complete. Communication systems based on quantum entanglement could provide instantaneous, unbreakable connections across vast distances, transforming how information travels through our expanding civilization. The investigation of antimatter and dark matter from the unique vantage point of space brings us closer to understanding the 95% of the universe that remains invisible to human observation. Specialized detectors aboard the station search for the subtle signatures of these mysterious components of reality, seeking clues that might unlock the deepest secrets of cosmic architecture. The data collected from these searches contributes to our growing understanding of how the universe evolved from the primordial simplicity following the Big Bang to the complex structures we observe today. Gravitational wave research conducted from orbit provides a stable platform for detecting the ripples in space-time itself, created by the most violent events in the cosmos. When black holes spiral into each other in distant galaxies, they create disturbances in the fabric of reality that propagate across billions of light years, carrying information about phenomena so extreme that they challenge our understanding of physics. The station's instruments contribute to a growing network of detectors that listen for these cosmic whispers, gradually mapping the most energetic processes in the universe. The biological research conducted in microgravity has revealed cellular processes that remain hidden under the constant influence of Earth's gravitational field. Cells behave differently when freed from the mechanical stresses imposed by gravity, revealing aspects of life that have remained invisible throughout the entire history of biological research. These discoveries influence our understanding of aging, disease progression, and the fundamental mechanisms that govern how living organisms function at the molecular level. Tissue engineering experiments in space take advantage of the three-dimensional environment that microgravity provides, allowing researchers to grow complex biological structures that cannot be created in terrestrial laboratories. Heart tissue, liver cells, and neural networks develop with architectures that more closely resemble natural organs when grown without gravity's constant downward pull. These space-grown tissues provide better models for studying human diseases and testing potential treatments than anything possible in ground-based research facilities. The study of aging processes accelerated by the space environment provides insights that benefit elderly populations worldwide. The rapid bone loss and muscle deterioration experienced by astronauts mimics aspects of aging that occur over years on Earth, but happen much more quickly in space. Understanding how to counteract these effects not only protects astronaut health, but also contributes to treatments for age-related conditions that affect millions of people as they grow older. Immune system research conducted aboard the station reveals how the body's defense mechanisms adapt to the stresses of spaceflight. Some crew members experience enhanced immune responses, while others show increased susceptibility to infections. These variations provide natural experiments that help researchers understand how environmental factors influence immune function, contributing to the development of treatments for autoimmune diseases and immune deficiencies. And so our journey through humanity's greatest achievement draws to a gentle close, but the story itself continues unfolding 250 miles above your head at this very moment. The International Space Station stands as living proof that when we choose cooperation over competition, when we reach beyond the boundaries of what seems possible, we discover that our greatest adventures lie not behind us, but ahead of us, waiting among the stars. Sweet dreams, fellow travelers in this cosmic dance.